Hello guys, how are you doing? Hope you're doing well. So this video is on the presentation mode, and this video I have prepared for 12th International Conference on Mathematical Modeling in Physical Science, which will be held in Belgrade, Serbia, from 28 August to 31 August. So in this, the title of the talk is Non-Minimal Interaction of Kessence Field with Dark Matter Fluid, and the collaborators are Anirban Chatterjee and Kaushik Bhattacharya. The outline of this talk is, first I'm going to introduce what is the Hubble tension, and then I'm going to introduce the interacting dark energy and the possible solutions. Then I'm going to introduce the action of actually interacting dark energy, and then I'm going to brief about dynamical system stability of some interaction, which is basically in this case the kinetic interaction, and then I'm going to complete this talk. So first of all, as we have entered in the precision measurement of a Hubble constant, so we have basically two ways to measuring the Hubble constant, which is from the indirect measurement and direct measurement. In the indirect measurement, we are taking the cosmic microwave background radiation with the different satellites, let's say Planck satellites and the ground-based satellites, and from which we are observing that the Hubble constant is lying between 66 to 68 kilometer per second per megaparsec. Now, if you are using the supernovae or type 1 supernovae or Cepheid variables, then from the direct measurement, we are getting that the Hubble constant is lying between 73 to 74 kilometer per second per megaparsec. So we are getting this Hubble constant from the lambda CDM model, and this is actually showing you that the lambda CDM model, which is assumed to be one of the perfect model, which is basically giving us a good fit with various data sets, having some trouble getting the Hubble parameter, and this discrepancy in getting the Hubble parameter is about 4.4 signal level, which is indicating that okay, this is a failure of the lambda CDM model. So what could be the alternatives of lambda CDM model? Well, there are vast models of alternatives to propose to elevate the Hubble parameter, out of which we are outlining few of them, like early dark energy. There could be some dark energy component during the radiation epoch, for which it can increase the Hubble, it can increase the rate of expansion, so that the Hubble tension, so the Hubble measurement that we are getting from the early universe can be increased, so that the tension between the direct and indirect measurement can be elevated. Now we can use the extra dark radiation component at the period of recombination by using the by altering the degree of relativistic component, so that again we can achieve the Hubble parameter up to 72 kilometer per second per megaparsec. Now we can also think that dark energy is no longer constant. The equation of dark energy is no longer constant, as we are seeing in the lambda CDM model, which is -1, but it can vary from different redshift. So for an example, the equation of the state of dark energy can become some complicated version of the dark energy, and which may eventually can reduce the Hubble tensor. On the other hand, there is maybe non-gravitational interaction between the dark matter and dark energy. So this interaction can play a role in order to achieve the Hubble tensor, elevating the Hubble tensor. On the other hand, maybe the gravity models that we are relying on, the Einstein-Hilbert action, is no longer the good one. So we have to somehow modify the gravity models, and on which we have the teleparallel gravity or FQ gravity. In teleparallel gravity, we have the metric which is not a torsion free. The torsion of the metric is no longer vanishes. On the other hand, the covariant derivative of the metric tensor is no longer zero in FQ gravity. Now in this talk, we are mainly focused on the interacting dark energy. So basically, interacting is invoking by hand at the level of our continuity equation, in which we are saying that all the matters, let us say we have dark matter and dark energy, the covariant stress tensor, the covariant derivative of the stress tensor is no longer conserved individually. Rather than there is an energy flow takes place between these two sectors by using some Q nu. If Q is coming out to be positive, then we can say that the energy is flowing from dark energy to dark matter. If it is negative, then vice versa. Now, these invoking of right hand term in such a way that the total component of stress tensor, the covariant derivative has to be zero. It means that whatever the components that is present in the universe, the covariant derivative has to be zero. Now, recently, Valentino et al. And their collaborators have shown that if we are modeling the interaction term as as it is comprised with some constant of chi, and then there is a rho de, and then Hubble parameter h, then using the Planck 2018 data, which is very recently released data from the CMBR, we found that H0 to be 72.80, which is again 1 sigma level, which brings the tension to 1 sigma level with the direct measurement. And chi is coming out to be minus 0.54, which hints that the energy is flowing from dark matter to dark energy, and this flow of energy from dark matter to dark energy is basically increasing the Hubble rate. And due to this increment of the Hubble rate, the discrepancy gets reduced from in the early universe to the late time phase. Now, the problem with the interaction, there is a lot of problem in the interaction. First of all, the interaction that we are studying is a phenomenological, and it has been introduced by hand. So there is a lack of interaction in Q, and because in most of the cases, people are using Q to be proportional to the energy density of the components, or maybe the Hess times. So so there is a lack of synchronization, and then there is a lack of physical motivation too of Hubble parameter, because the interaction depends on universal expansion rate. Hess depends on the universal expansion rate, which is introduced for the mathematical simplicity rather than any physical motivation. One expects interaction to be played at each event rather depending on the global behavior of the universe. However, the recent data shows that, okay, the interaction has to be some h. So it is when you understand, it is really understand that how the interaction is coming at this interaction. How the h is coming at the interaction level. Now, on doing the perturbation of the background metric, we are finding that there could be instability in the dark sector, in which this instability can be removed by tweaking by hand, tweaking the parameter, tweaking the interaction by hand. So, what could be the possible solution? We understand that maybe the interaction parameter can be derived from the action principle. So the action can be written as the action for general relativity, action for the gravitation sector, action for the metric dark matter and dark energy, and there is an interaction Lagrangian which is comprised with the dark matter and dark energy. Now, if you are taking the variation with respect to metric, then we have the Friedmann equations and the continuity equations. Now, the Friedmann equation, we can see that there is an additional term arises as rho interaction and p interaction. So this rho interaction and p interaction is coming from the interacting Lagrangian, which was completed, which was no component like this in the former case. On the other hand, we have following constraint, because we are understanding that the total energy density of the components has to fall. Okay, because the total stress tensor is covariant, or the covariant derivative of the total stress tensor has to be 0. So the constant relation is coming from this interaction Lagrangian is rho dot plus 3h rho interaction plus p interaction and qd plus 2m. So it will so with this we can find that, okay, rho m dot plus 3h rho m. So it will simply constant this the form of qm and qd as previously. So one can show that if we are using any linear transformation such that the total density, because in the former case we have rho m plus rho de, which is making the total energy density. In the other hand, we have total energy density comprised with rho m rho de plus rho index. So we understand that either in any picture, the total energy density and total pressure has to be remain invariant. So if you are using any such linear transformation which makes energy density and pressure to be remain invariant, then we can say that these two pictures are equivalent. Although these two pictures are coming out to be equivalent, then however there is a great deviation in the Friedmann equations, as well as the pressure of in the later case has also deviated vastly from the previous. Now, what could be the action of interacting dark sector? Because previously we have used for the toy model. However, we are using the interacting dark sector in a realistic form, where the first term is showing the action of Einstein-Hilbert action. On the other hand, the second term is showing you the action of relativistic fluid, in which the rho is the energy density of the matter, which depending on the number density and the specific entropy, which is entropy per unit per particle. And the J mu is the particle flux density, which is multiplying with the phi theta and BA alpha. So these parameters are the Lagrange parameters, and the comma is representing the derivative with respect to the mu's and all these things. So J mu is contracting with these Lagrange parameters. On the other hand, we have the field Lagrangian, which is having the phi and x over here is the field velocity. So it is a derivative of the field, and because of this x, the field Lagrangian becomes non-canonical. On the other hand, we have we have the two interaction. One is called kinetic interaction and derivative interaction, which we are going to study separately. So in the kinetic interaction, the FC is a function of ns phi comma x. On the other hand, the derivative, apart from the function of field and fluid parameter, the field velocity is contracting with the particle flux density. So the particle flux density have the following form, and the u mu is contracting and giving you the -1. So if you are taking the variation with respect to the G mu nu, we have the Friedmann equation in the background of FLRW metric, which is basically 3h square is equal to the energy density, and the second Friedmann equation is giving you the pressure relationship. So if you try to find out the pressure and energy density, we have to take a variation with respect to the metric, and we are going to compare these components of the stress tensor of the perfect fluid. So T mu nu is written for the perfect fluid, and by comparing with the field and fluid, or for the kinetic coupling and derivative coupling, we can identify the rho interaction and P interaction, similarly for rho phi and P phi. And here x is the derivative of the field, so x is equal to phi dot square. So x cannot be negative, x has to be remain positive. Now, if you are taking the continuity equation, the covariant derivative of the stress tensor in the kinetic coupling case, it is coming out to be derivative of the field term. So there is no any Hess term is coming if the interaction is just only a function of field and fluid parameters. On the other hand, if apart from the interaction, if the field velocity is contracting with the particle flux density, then we have the interaction form at the continuity equation having some Hubble parameter, which is you can see over here 3h phi dot, and there is a derivative arising with respect to the fluid term. Now, similarly, if I take the variation of the action with respect to delta phi, so it will yield the field equation. So field equation will getting modified because of the presence of the interaction parameters. Now, similarly, we can get different thermodynamic equations, because we have the J mu s, and these are the free parameters in the Lagrangian, and taking the variation with respect to J mu s, phi theta, var phi theta, beta and alpha, we have several equations which is basically generalized with the chemical potential and the temperature of the equations and all and so on. So one of the constant relation we are getting from the variation of phi and theta, that the entropy in the dark matter, the entropy is remain constant in the dark matter fluid, and as well as the dark matter and particle density is falling as the universe is expanding. Now, in order to constrain the parameters, and in order to understand that what could be the dynamics of the system, we are using the dynamic system stability analysis corresponding to the kinetic interaction. So first of all, I'm going to give you the brief idea of what is dynamic system stability. Is that in order to study any system, we have to first define the dimensionless variable. And for this case, the dimensionless variables are x, y, sigma, z, and omega phi. X is capturing the field velocity. Y is corresponding to the field potential. Sigma is the fraction density of the fluid, and z is capturing the interaction parameter, and omega phi is giving the fraction density of the field. Now, for the kessence Lagrangian, the Lagrangian is becoming minus v phi into fx, and fx had the following form, which is derivative from the string theory, which is minus x plus x squared, and we are studying the kessence with the inverse square type of potential, which is delta square by kappa square phi square, and delta is a free parameter over here. And following the first Friedmann equation, we have the following constraint, because the sigma squared is representing the field fraction density, which cannot be negative. So it has to be between 0 to 1. On the other hand, we can express several cosmological observable parameters like equation of a state. For an example, equation of a state has to be gets modified. We are having the P total. P total is the total pressure or to the ratio of total energy density. On the other hand, we have the sound speed, and this sound speed is defined as the pressure perturbation in the field to the density perturbation in the rest frame of the field, and this has to be between 0 to 1. And now because of the interaction parameter, it gets analyzed, so we have to take the derivative of p total and rho total with respect to x. So in order to have the model to be stable in the background as well as the perturbation level, c square cannot be negative. It has to be between 0 to 1, and in some nonlinear theories it can exceed 1, so which is again acceptable in some nonlinear theories, because the kessence is again non-canonical one, and in non-canonical it has been observed that the sound speed becomes superluminal. Now, after realizing these dimensionless variables, we can invoke, try to construct the autonomous equation by taking the time derivative of x, y, and z. So x, y, and z are three variables for which, using which we can express each and every observables in these parameters. So x, y, z, and because of this x prime, y prime, and z prime, the autonomous equation will become having the phase space of 3D. Now, in order to find the critical point, we can equate x right hand side of x prime, y prime, and z prime to be 0, and it will yield the critical points. And in order to find the stability, we have to first construct the Jacobian matrix like this, and for 3-dimensional phase it will be 3 cross 3 matrix, and we have to find the eigenvalues at those critical points. If the real part of the eigenvalues is coming out to be totally positive, then it is the corresponding critical point becomes unstable. If the real part having the total negative sign, it becomes stable, and if we have the alternate sign, the critical point becomes saddle. It means that it is saddle means that the critical point will first behave like an attractor point, and then it will, and all the trajectory will repel from it. So it is showing you the saddle behavior. Now, in order to study the kinetic coupling, we are taking the model of the exponential type in which m is some kind of constant. So m has the mass constant, rho is energy density of the fluid, and phi over kappa making a dimensionless parameter, and having the free parameter of n e to the power beta x. So we have the following parameter space, like 4-dimensional parameter space, epsilon, m, beta, and delta. Now, in order to quantify these parameters, that what could be the range of these parameters, so we are first finding those critical points. Now, these critical points, we are taking those critical points at which the z, because z is capturing the interaction parameters, z is no longer 0. If z becomes 0, then it is becoming again the minimal coupling. So we are not interested in that case. So those critical points for which z is not 0, we are taking and we are trying to estimate. We are trying to analyze those critical points. Now, if you take those critical points and we try to estimate the total equation of state, we found that the total equation of state only depends on m and epsilon, and based on the total equation of state, because if total equation of state lies between -1 to -1/3, which is representing by the green region, so it shows that the model is giving you the accelerating region. On the other hand, the blue shows the phantom region, because the model can also cross the -1 barrier, phantom barrier. So there is a relation there. In that way, we have constraint m and epsilon. Now, on the other hand, if that critical point is basically showing you the late time behavior, it means that at this point, the fraction field density has to be dominating over the fluid equation, and as well as the eigenvalue has to be negative, with sound speed has to be between 0 to 1. And when we are analyze these conditions, we have found that if we are taking epsilon and m in the green region, then we can find the overlapping region. If so, in the bluish region we have the eigenvalues, and in the gray region or in the some yellow region we have the field equation as well as the sound speed. So in the bluish region, it shows that the field density is between 0.65 to 1, and sound speed is between 0 to 1. And the blue region, all the eigenvalues is all the eigenvalues are negative. So if you are taking epsilon to be 0.1 and some parameters delta to be 20, m minus 1, minus 0.1, and beta n minus 1, then we are getting the accelerating stable solids. Now we have compactified the phase space, because z is not a compactified variable. In that way, the phase space is non-compactified. So in order to compactify the phase space, we have transformed the origin variables x, y, z into capital X, Y, and Z. And from here we are getting, we are representing all the critical points over here: A1, A2, A3, A4, and A5. A5 is the critical point at which the interaction is no longer vanishes, and it shows that all the it shows a global attracting behavior because the trajectory that is originating from some point at the phase space is eventually attracting towards a5. And now in the right hand side, we have trace out the evolution of the several parameters, several cosmological parameters, such as the fraction field density in the blue. Red represents the fluid parameter or fluid density, and equals total equation of the state in the green, and the dotted orange color is showing you the evolution of the sound speed, the effective sound speed. So for n is ranging from minus to plus. So in the minus, it is showing you the asymptotic past, and in the plus, it's showing you the asymptotic future. And n is equal to 0 is giving you the giving us the present epoch of the universe. So if you're looking at the very past universe, the kessence is behaving like a radiation density, because at this point we have omega total be 1 by 3 and c square is also 1 by 3. And at this point, the fluid density is completely vanished. And so this kind of interaction is showing you that the kessence can behave as a radius. And as the system is evolving, the dark matter is dominating over the kessence field density, and omega total becomes 0. On the other hand, as we are moving at the present epoch, we are seeing that the dark matter is vanishing, is getting suppressed by the field, and the field density is coming out to be approximately 0.7 and so on. And as we are going in the asymptotic future, the field density remain dominating over the fluid density, and this late time epoch, the interaction is no longer vanishes and the interaction remains non-zero. So in order to conclude it, the coupling introduced at the Lagrangian level generalizes the interaction and making it easy to identify instability at the perturbation level. So it is by using the Lagrangian level, we can identify each and every instability at the perturbation level. Now we have considered two types of coupling. One in which interaction is a function of both of field and fluid parameter, and using dynamical system stability analysis corresponding to exponential interaction form, the model demonstrates stable accelerating solution during late time phase. And in another, we have the field velocity couples with particle flux density, which is resulting in Hubble parameter in the continuity equation. Here are from following references you can go through for important references and their references theory. Thank you very much. This is Aminado Cap signing out, and I'm going to discuss in more detail in some different video. Thank you very much.